Good afternoon. My talk is about implementation aspects of post-quantum cryptography. This post-quantum cryptography is an active area, so many researchers are working in this area. As a consequence, there are more than one stories of implementing post-quantum cryptography. In this talk, I will present my story of implementing lattice-based post-quantum public key cryptography. Every day we interact with many websites and we exchange confidential information. For example, I often go to Amazon to buy things, and there I am not scared of using my credit card because I see this lock symbol followed by secure and HTTPS. They tell me that I have made a secure connection with the genuine Amazon website. So how does HTTPS protect the internet? The first step is authentication of the website server. In this phase, the browser of the client can verify the authenticity of the server using a cryptographic technique known as digital signature. Then the next step is key exchange. In this phase, the two parties, they agree on a common key. The final step is establishment of an encrypted communication link. In this phase, the two parties, they use their common key with some symmetric algorithm, for example AES, to encrypt every data they transfer over the wire. Since the data is encrypted, an adversary cannot learn anything from the encrypted data. The three steps are listed here. The first two, verification of the website certificate and key agreement, they use public key cryptography. I investigate implementation aspects of next generation public key cryptography. The most popular present day public key algorithms are the RSA crypto system and elliptic curve or ECC crypto system. They are protecting our public infrastructure. However, source algorithm running on a powerful quantum computer can break both RSA and ECC easily. So what is the state of art in quantum computing? Last March, March 2018, Google demonstrated a 72 qubit quantum computer. This is a bit faster than our present day computer. However, to break the RSA algorithm, a million qubit quantum computer is required. So this quantum computer is not powerful enough to break RSA crypto system. Quantum computing experts, they anticipate that a powerful quantum computer to break RSA algorithm will be feasible within next 10 to 15 years. Keeping in mind recent progress in quantum computing, the American standardization body NIST, they recommended a gradual transition towards quantum attack resistant post quantum cryptography, and they started a standardization project known as NIST post quantum cryptography standardization, the deadline of which was November 2017. There are several candidates. Majority of them use the learning with errors or LW problem as the foundation problem for constructing cryptographic scheme. This LW or learning with error is a lattice problem. To understand this problem, let us recapitulate our high school algebra classes. We are given linear equations with unknown, say x and y, and we are asked to solve the unknowns. Now when I moved to the university, I came to know that there is also a matrix vector equivalent for the system of linear equations. Now if the number of unknowns is small, then we can compute or solve the unknowns easily by hand. When the number of unknowns is large, say n, and if there are m number of linear equations where m is greater than equals to n, then we can use a mathematical technique known as Gaussian elimination to solve a system of linear equations. This is easy, and you can program Gaussian elimination on a computer, so it can be computed easily. However, the situation changes if small errors ei are added to every linear equation. Then it becomes computationally infeasible for a powerful classical computer as well as a powerful quantum computer to solve the unknown secret S. This problem is known as the learning with error or LW problem. You have to learn or solve S in the presence of errors. That's why it is learning with errors. Similar to the LW problem, there is also a problem known as learning with rounding or LWR. In case of LW, errors are added. First they are generated and they are added to every linear equation. In case of LWR, we do not need to generate errors. The errors are implicit. So what is done here? First, the matrix is multiplied with the secret, and then the coefficients of the result, they are scaled by multiplying them with p and then dividing them by q, where q is larger than p. Since q is larger than p, the scaling operation performs data compression, and this data compression introduces noise. This noise is the rounding noise. So, in case of LWR, the noise is generated deterministically and it is also implicit. We do not need to sample the errors like LWE. So, LWR requires less randomness, and it can also result in more efficient crypto system if the scaling operation, which is done using multiplication by p and then division by q, is also cheap. In that setting, LWR can be more efficient than LWE. Anyways, we can use LWE or LWR as a black box to construct a key exchange scheme, which works like a Diffie-Hellman style key exchange. This slide shows the basic idea of LWE based key exchange scheme. There is a public matrix A and two parties, client and the server. The client generates two error vectors S and E from a discrete noise distribution or error distribution, and then she multiplies the matrix A with her secret S and then adds the linear adds the vector E with it and gets a vector B. B is sent to the server. The server does similar calculations and computes B prime, which is sent to the client. Now, the client multiplies the transpose of B prime with her secret S and gets one coefficient phi. Similarly, the server multiplies the transpose of its secret S prime with received B and gets the coefficient V prime. Now, these two coefficients V and V prime, they are almost the same. They differ by a small amount of noise. So, the two parties, they agree on a noisy shared secret and the noise is small. Now, what they can do now is they can apply a threshold decoding algorithm on their respective coefficients to extract a single key bit. Now, this decoding algorithm can be designed in such a way that with high probability the two parties can agree on a common key bit. Now, if their goal is to establish a 128 bit AES key, then they can repeat this process 128 times. Each time they can extract a single key bit. So, this is the basic idea of LW based key exchange, and the security of this key exchange scheme relies on the hardness of the LW problem. Now, my goal is to design such crypto system efficiently. So, let us find what are the most important building blocks. One thing is we need to compute or generate S and E in the client side from a discrete noise distribution. So, we need a noise sampler. Then we also need to compute matrix vector multiplication, and we also need to compute addition of a vector. Addition of a vector is a linear operation, so it is cheap. The major building blocks are noise sampling to sample S and E vectors and to perform matrix vector multiplication. First, I will talk about how error or noise sampling is done, and then I will go to matrix vector multiplication. In lattice based cryptography, the error distribution is typically a discrete Gaussian distribution. When I started my research in around 2013 in this area, it was not known how to sample from a discrete Gaussian distribution efficiently and securely. We designed an efficient and lightweight discrete Gaussian sampler based on a random walk on an unbalanced binary tree approach, which was pioneered by Donald Knuth and Andrew Yao in 1976. The biggest advantage of this approach is it requires minimum entropy, and you know generation of random bits can be expensive, particularly on resource constrained platforms. Now, I will explain the Knuth-Yao random walk algorithm with a toy example. Let us consider a small sample space S consisting of only 3 points 0, 1 and 2 with probabilities P0, P1 and P2. We can write down a matrix for the probability bits. This we call probability matrix. Now, for a given or known distribution, the matrix is known, and corresponding to this matrix there is a rooted binary tree. This tree represents the distribution. It is called discrete distribution generating tree. It consists of two types of nodes, intermediate nodes with symbol I and terminal nodes. These terminal nodes contain the values of the sample space. So, here the sample space consists of 3 values 0, 1 and 2. So, it has 0, 1 and 2 in its terminal node. A random walk starts from the root of the tree, and for each jump it uses a random bit. If the bit is 0, then it chooses the left branch. If the bit is 1, then it chooses the right branch. Here is an example. The bit is 0, so left branch, intermediate node, the walk continues. Another bit is generated, which is 0 again. So again a left branch is taken. This is an intermediate node. Finally, another bit is generated, which is 1. A right branch is chosen, and in this case, the visited node in the tree is a terminal node. So the walk stops, and the value of the node is the output of the random walk or the sampling operation. So 0 becomes a Gaussian distributed sample. Now this process can be repeated many number of times. Suppose we want to generate a vector of say 256 coefficients, then we can repeat this process 256 times, and then we will get a Gaussian distributed vector. Now, to implement the original Nuthia random walk algorithm as a binary tree traversal, we will require dynamic memory allocation, pointer arithmetic. These kind of operations can be supported only by kind of advanced computer architecture. We proposed and implemented an 18-line on-the-fly lightweight algorithm which can compute Gaussian distributed samples using small counters and a small comparator circuit. Now these counters and comparators, they are only a few bits wide. When the distribution has small standard deviation, that is the distribution is quite narrow, our algorithm results in optimal space and time requirement, and it can be implemented on both software and hardware, including resource constraint platforms. For example, on a Xilinx FPGA, it consumes only 1% of the resources. And here this is ARM CortexM4 microcontroller. Here also the implementation is very lightweight, and the algorithm is also quite fast, only 28 cycles in software. Now this is about efficient and lightweight Gaussian sampling. Now there is a problem. The problem is the random walk is performed along an unbalanced binary tree, so the terminal nodes are at different levels of the tree. As a consequence, this random walk has variable execution time. For example, if the random walk visits this node, then it will take 3 jump operations, but if it visits the end node, then it will take 2 more jump operations. So there is variation in the execution time. Now consider an adversary who is observing physical properties, side channel properties of the algorithm. For example, a device which is computing Nuthia random walk, and the adversary is observing electromagnetic field intensity radiation from the device. So here is a plot for 2 different sampling operations, blue and red. The blue operation takes fewer cycles than the red sampling operation. Now, by observing the number of cycles, an adversary can guess which sample value is generated, because the distribution of the tree is known, is public. So the sample values can be estimated or guessed. Now this is a big problem, because the LW problem in the ideal world assumes that both S and E, the secret and the error vector, are unknown. Now timing leakage from Nuthia random walk or sampling operation reveals information about the error coefficients. So E becomes green from red, it becomes kind of known. Now it requires simple operations for an adversary to compute the secret vector S. Implementation of a constant time Gaussian sampling remained an open problem for several years, and timing attacks on Gaussian sampling forced cryptographic protocol designers to use alternative methods at the cost of increased communication bandwidth and computation time. Now I will tell how we designed constant time discrete Gaussian sampling. The output of the random walk is completely determined by the input random string. For example, if the random string is 001, then the sample value is 0. If it is 010, then it produces 1. So it's a mapping from random string to sample string. And this mapping is known because the distribution is known. So for a known mapping, what we can do is we can express the bits of the sample space as Boolean equations of the input random string. This is possible because the mapping is known. So, we can write down the Boolean expressions for each of the sample bit. Now, if we can evaluate these Boolean equations in constant time, then we can get a constant time discrete Gaussian sampler. So, that is what we did. We designed a fully constant time discrete Gaussian sampler by performing Boolean decomposition, and in the low level we also applied bit slicing to improve its efficiency. So, bit slicing offers parallel processing. In the high level we applied Gaussian convolution lemma, which enables you to split a Gaussian sampling from a wide Gaussian distribution into multiple samplings from a narrow distribution. And for a narrow distribution, we can easily do this Boolean decomposition and bit slicing. Overhead, when this constant time sampler was integrated in the Falcon signature scheme, Falcon is a scheme in this second round phase of the standardization project. It is a signature scheme. When the constant time sampler was integrated in it, it resulted in 33% extra computation time. However, this sampler was for 128-bit precision, so there are 128 random bits. A few days ago, the Falcon team contacted us. They said 128 bits is not needed, 78 bits of precision is enough. In that case, if 78 bits of precision is used, then it will be a mapping from 78-bit random string to sample space, and it will reduce the overhead to say only 20%. We hope our constant time Gaussian sampler will enable design of more efficient signature schemes in the future. So, the error sampling is done. The next operation is matrix vector multiplication. This has order of n square complexity. Here are performance figures for the Frodo key encapsulation scheme. It uses matrix dimension 640 to achieve 100-bit quantum security and matrix dimension 976 to achieve more than 150-bit quantum security. So, these are cycle counts for Frodo KM running on ARM Cortex M4 microcontroller. This is a popular microcontroller for implementing post-quantum algorithms, and NIST also wants performance figures on this platform. So, all operations, key generation, encapsulation, decapsulation, they require more than 80 million cycles. If the device is run at 24 megahertz clock frequency, then each operation will take more than 3 seconds. This is rather slow. The problem is Frodo performs expensive matrix vector multiplications many number of times. So, it is slow. There is a way to improve efficiency. Now, in case of LWE, what happens is there is a public matrix A, and the elements of this matrix, they are uniformly random. Now, consider a special LWE in which only one column is uniformly random. Rest of the columns are just negacyclic rotations of the first column. So, here is the rotation, then another rotation by 2 positions. In this way, this gives another matrix. So, this matrix has a special structure. The advantage of this special LWE is that using such matrix, expensive matrix vector multiplication reduces to cheaper polynomial arithmetic. As a consequence, it results in a better or faster computation time, and it also saves some space. The arithmetic is done always in a ring, a polynomial ring. That is why it is called ring LWE. Now, the main problem is no more matrix vector multiplication, it is only multiplication of 2 polynomials. Now, I will talk about how to perform multiplication of 2 polynomials efficiently. There are several algorithms. Fast Fourier transform or FFT based algorithm has the least asymptotic time complexity n log n. So, initially we chose this algorithm due to its asymptotic time complexity superiority. So, how FFT is used to do polynomial multiplication? Suppose we have 2 polynomials ax and bx, each containing n coefficients. Then the polynomial is first represented as an array of n coefficients. Then n number of zeros are appended in its top portion. It gives an array of 2n coefficients. Then 2n point fast Fourier transform is computed on it. It gives Fourier domain representation of the input polynomial. Similarly, for the other polynomial bx, we get its Fourier representation by computing 2 endpoint fast Fourier transform. Now, in the Fourier domain, multiplication is a coefficient-wise linear operation. So, we compute 2n number of coefficient-wise multiplications and we get this array C. C is actually the result of the polynomial multiplication, but it is in the Fourier domain. So, what we need to do is to compute 2n point inverse Fourier transform, and this gives the result in the polynomial domain again. This is the basic idea of fast Fourier transform based polynomial multiplication. However, there is a problem. FFT involves real number arithmetic, and these real numbers, they introduce approximation error. Number theoretic transform or NTT is a generalization of fast Fourier transform. It uses only integer arithmetic modulo q. Now, there are two requirements. N, which is the number of coefficients, should be a power of 2, and modulus q should be a prime with the relation that q is congruent to 1 modulo n. A special optimization known as negative wrapped convolution is possible if q is also congruent to 1 modulo 2n, not just n. In case of negative wrapped convolution, we need to compute only n point entities instead of 2 n point entity. In this way, using negative wrapped convolution, we can get more than 2x faster computation. However, negative wrapped convolution has additional overheads. It requires scaling of the input polynomials and also post scaling. Now, all these scaling operations, they have order of n complexity. We improved efficiency of negative wrapped convolution based polynomial multiplication. We first proposed a mathematical optimization which eliminates the pre-scaling operation completely. So, it gives zero cost pre-scaling operation. The biggest performance optimization came from memory access reduction, which I will describe now. But before that, I will briefly describe how NTT algorithm works. NTT algorithm has 3 nested loops. This is the iterative version of the NTT algorithm. In the innermost loop, an index is computed from the 3 loop variables m, j, and k, and then there is a function called butterfly. It processes 2 coefficients with index difference m divided by 2. So, the coefficients are here, and they are assumed that they are stored in a sequential memory, for example, SRAM. So, 2 coefficients, they are read from the memory and they are processed inside the butterfly core, and 2 new values are computed, and finally, they are written back to the memory. Here is an example. Entity starts with m equals to 2. So, the index difference is only 1. So, the butterfly is computed on A0, A1, then A2, A3. In this way, finally, on the last pair, n minus 2 and n minus 1. Then the m loop finishes. The next is m equals to 4, because m always increments by factor of 2. So, m becomes 4 from 2. Now, the index difference is 2, because it is always m divided by 2. So, in the j loop, first the coefficients A0, A2 are processed, then A4, A6 are processed. Basically, all even indexed coefficients, but with index difference 2 are processed in the first iteration of the j loop. Then in the next iteration of the j loop, all odd coefficients with index difference again 2 are processed. So, this is the idea of NTT algorithm. The outermost loop m iterates for log n number of times, where n is the number of coefficients, and every time or every iteration, one coefficient is processed only once. So, each coefficient is processed log n number of times throughout the entire NTT algorithm. Now, I come to the memory access problem. Our memory is sequential because this is SRAM, so it can produce one coefficient and consume only one coefficient at a time every cycle. Now, what is this butterfly operation? This butterfly operation processes 2 coefficients with index difference m divided by 2. One coefficient is multiplied with a constant omega, then the result of the multiplication is added to or subtracted from the other coefficient. Then this gives 2 new values of the coefficients. Now, these coefficients are written back in the memory. Since memory is sequential, we we read two coefficients in two operations, two read operations. Now the butterfly operation in hardware we can compute in parallel. We can keep a dedicated multiplier, adder and a subtractor and compute the entire step in one computation cycle. However, we need to write back two results, so we need to perform two write operations. Now what is happening here is we are performing two read operations, one computation and two write operations. So this brings producer consumer problem into picture. The memory is the slower, it is becoming the bottleneck here. The processing unit is remaining idle for one clock cycle, and as a consequence it is not fully utilized. Now I will talk about its solution. So the problem is that we are accessing one coefficient at a time. We have small coefficients, small enough so that we can keep two coefficients in a single memory word. For example, say A0, A1 residing in the same word. In that case, what will happen? We can read both A0 and A1 from the word using a single read operation, so only one read cycle. Then we can apply this butterfly core on the coefficient pair. We can compute the new values and then we can write them back again in the memory, because memory can contain two coefficients in a single word in one cycle. So it's basically one cycle for reading, one computation, one write. In a pipelined arithmetic unit or pipeline processor, we can compute all these operations in pipeline. So there will be no bottleneck. Everyone is fully utilized. This looks fine, but there is a problem. The problem happens when m becomes 4 from 2. Now the index difference becomes 2. Previously it was 1, it has become 2. So we need to process A0 and A2, then A4, A6. Now here A0 and A2, they are in two different memory words. So the producer consumer problem again comes back into the picture. We will have to perform two read operations because the required coefficients are in two different memory words. So this doesn't solve the problem. We proposed a technique. In this technique we process four coefficients, that is two coefficient pairs together. So we read two coefficient pairs from the memory, we perform two read operations and store them in the internal registers of the arithmetic unit. So now they are residing in registers of the arithmetic unit. Next we apply this butterfly circuit twice on the two coefficient pairs. So this gives two new coefficient pairs. Next what we do is, previously we are writing back A0 and A1 in the memory, A2 and A3 in the memory. Instead of horizontal packing, we pack the coefficients vertically. So we pack A0, A2 and write back in the memory A1 and A3, and here they are stored. The advantage of this approach is, in the beginning the index difference was 1. Now when we are writing back, the index difference is becoming 2. So the data which was initially arranged for m equals to 2 of the outer loop becomes ready for processing in the m equals to 4 loop, because now the index difference is 2, and in the m equals to 4 loop we need to process coefficients with index difference 2. So in that loop we will readily get the required coefficients from the same memory address. So we are performing two read operations, two computation and two write operations. Again everything is balanced, so we can process them nicely in a pipeline data path. Okay, so results. Before we started our work, it was this pre-scaling, then entity, then post-scaling operation. We removed the pre-scaling overhead, so it's only now this. And finally we also reduce the number of memory access by half. So again there is a reduction by factor of 2 in the overall computation time. So this was our result in 2014. 1 year later, researchers from Microsoft, they also eliminated the post-scaling operation. So now it is only this much. From the algorithm, we designed an efficient hardware architecture for computing polynomial arithmetic, polynomial multiplication. The coefficients are stored in the RAM. For example, BRAM on an FPGA. Here is the arithmetic unit. It consists of a multiplier, subtractor, and adder circuit. All these computation blocks, they are heavily pipelined. Pipeline registers are shown in as horizontal lines. There are also several other registers to support the pipeline processing of the entire data path. There is also a control unit to control this entire processing element. Now, from the heavily optimized entity arithmetic unit and from the discrete Gaussian sampler, we designed an instruction set coprocessor which supports 9 instructions, and this coprocessor can be used to perform ring LW encryption and decryption operations. It can compute over 50,000 encryptions per second and 100,000 decryptions per second, and it consumes only 1.3 thousand lookup tables, less than 1,000 flip-flops, 1 DSP multiplier, and only 2 block RAM slices on a Xilinx Vertex 6 FPGA. So, how does it compare to classical elliptic crypto system on a similar platform? So, here are results of an elliptic curve for binary field from CHES 2012. It computes over 40,000 encryptions and 80,000 decryptions per second, sorry, less than. And using ring LW cryptography, we can compute encryptions and decryptions faster. So, computationally it is better. Area wise, the ECC processor requires 18,000 lookup tables and more than 5,000 flip-flops. Here it is only 1.3 thousand lookup tables and less than 1,000 flip-flops. However, it requires DSP multiplier and block RAMs. The disadvantage in ring LW based cryptography is that we need to process polynomials, and that is why we need to store polynomials in the chip. So, we need large block RAMs. In case of elliptical cryptography, we need to process elements containing say 256 bits. So, area requirement or memory requirement is less. We also implemented the algorithms on software, for example, on CortexM 32-bit microcontroller and also on 8-bit AVR platform. There also we obtained order of magnitude faster computation with respect to elliptical cryptography. Okay, so that was efficient implementation of ring LW cryptography. Now I will talk about how we protected ring LW cryptography, specifically the decryption operation using masking scheme. The decryption involves 2 major steps. First thing is here C1 and C2 are the 2 ciphertext components. S is the secret key. We assume that all of them C1, C2 and S, they are in the entity domain. Then we need to compute a linear polynomial multiplication C1 times S. Since they are all in the entity domain, this operation is linear, and in the end we need to compute an inverse entity operation to get a polynomial m tilde. Then in the end we need to apply a threshold decode algorithm on m tilde to receive the message vector. So, this is the result of the decryption operation. So, here we need to protect the secret S, and we also need to be careful about the threshold decode algorithm because we are applying masking scheme. Now, I will talk about the core idea. So, in step 1 we are computing this. Now, arithmetic in the entity domain is linear. So, what we can do, we can split the secret S in 2 random shares, S prime and S double prime, and then we can distribute the computation which is done during decryption into 2 random computations. So, we are applying masking scheme, we are distributing the computation in 2 shares and making them independent of each other. The final step is threshold decoding algorithm. In this phase, we need to be very careful because this threshold decoder should not compare the 2 shares. How this decoder is designed involves a lot of low level tricks. I will not discuss them. You can see the paper for more detailed information about the mask decoder. Actually, the implementation and design of the mask decoder is the most challenging part in masking ring LW scheme. This is also a reason why it results in 2.5 times slowdown in the computation of ring LW decryption. Okay, so conclusion so far, ring LW based cryptography is efficient in both hardware and software, but there are security concerns because ring LW uses the special structured matrix which is generated from a single column. Some cryptographers, they are skeptical about the security of ring LW due to the presence of this special structure. So there exists a better solution which interpolates between standard LW, which uses matrix arithmetic, and ring LW, which uses polynomial arithmetic. This is called module LW. In case of module LW, the big matrix consists of several small matrices. Each matrix is generated from negacyclic rotation of its first column. Now, in such a case, in case of module LW, the entire operation includes matrix arithmetic as well as polynomial arithmetic, because every such thing arithmetic is a polynomial arithmetic. So, it is a matrix of several polynomials. In this way, module LW inherits security from standard LW because it has matrix structure in it, and it also inherits efficiency because it performs polynomial arithmetic. Normally, the dimension of the matrix is small, the polynomials are large. So, the overhead of doing quadratic complexity matrix arithmetic is small because the dimension of the matrices are small. We have participated in the ongoing NIST post-quantum cryptography standardization project by submitting a module LWR based key exchange scheme called Saber. Saber has moved to the second round of the standardization project. It's a nice collaboration between electrical engineer and mathematics team. Saber has been designed not just considering security aspects, it has been designed considering implementation aspects too. That's why it results in both security and efficiency. Saber uses module LWR problem, and all polynomials here are always of 256 coefficients. They are of fixed length, 256 coefficients. Since the polynomials are of fixed length, it enables design of a heavily optimized polynomial arithmetic operation or polynomial arithmetic core. Flexibility is obtained in the higher level, that is in the matrix level. 2 by 2 matrix gives light saver, 115-bit post-quantum security. If we change the matrix dimension to 3 by 3, we get 180-bit post-quantum security. And using 4 by 4, we can get more than 240-bit post-quantum security. This is known as fire saver. So, in the code, there is a parameter which is the dimension of the matrix. Just by changing the matrix, the dimension to 2, 3 or 4, we can get various security levels. So, this offers tremendous flexibility, and at the same time efficiency is maintained because the arithmetic on polynomials, they are always of fixed length. So, the parameters for Saber, polynomials are always of 256 coefficients, flexibility is in the matrix dimension 2 by 2, 3 by 3 or 4 by 4. Now, the question is how to choose the two scaling coefficients P and Q. I will come to that. Before that, I will describe how some of the features of it. Saber uses learning with rounding problem. There is a coefficient which is uniformly distributed in 0 to q minus 1. Now, there is this scaling operation. If P does not divide Q, then the scaling operation will introduce rounding bias, and this can have implications on the security. To do efficient entity arithmetic, we need to work with a prime modulus. So, in that case, Q will be prime, but if we choose Q prime, then P won't divide Q, and that will introduce rounding bias. So, we have two options. One option is to use entity based polynomial arithmetic. In that case, we have to use prime Q. The other option was to respect the implications of rounding bias on security and choose power of 2 modulus. In that case, both P and Q will be power of 2. So, P will divide Q, and we won't have rounding bias. However, if we choose power of 2, then we cannot use entity, but we have advantage, 2 advantages at least. One is we don't need to perform modular reduction because modular reduction is free in power of 2 modulus, and rounding also becomes easier. We are still exploring other advantages of using power of 2. So, Saber uses power of 2 modulus for both P and Q. Now, we cannot use entity-based fast polynomial arithmetic, so you have to use some generic polynomial multiplication algorithm, for example, say Kasuba multiplication, which does not depend on specially chosen prime or specially chosen modulus. So how does Kasuba multiplication works? Suppose we have two polynomials, each having 256 coefficients. Then it follows a divide and conquer approach. It splits large multiplication into three smaller multiplications having only half-sized polynomials. So there will be three 128 coefficient polynomial multiplications instead of one 256 coefficient polynomial multiplications. Another algorithm is known as Tomb-Cook multiplication. It is a generalization of Kasuba multiplication. In this case, we can split the input polynomials in arbitrary ways. For example, we can use Tomb-Cook 4 ways, and we can split 256 coefficient polynomial multiplication directly into 64 coefficient multiplications. Now, if we use Tomb-Cook 4a and we use 64 coefficient polynomial multiplication, then we will have to compute 7 such multiplications. If we use Kasuba multiplication, then in this level we will have to compute 9 multiplications. So, Tomb-Cook multiplication is faster than Kasuba multiplication. How Tomb-Cook 4a works? The first step is splitting. It splits the input polynomials into 4 64 coefficient polynomials. So, A consists of 4 polynomials, A0, A1, A2 and A3. Similarly, B consists of 4 polynomials. Then there is this evaluation phase. In this phase, linear operations are performed, for example, scalar multiplications, additions, and then 7 polynomial multiplications are computed. This part is the costliest operation. Finally, we have this interpolation phase. In this phase, only linear arithmetic is done along with some scalar division and scalar multiplication operations. Now, here this division by 24 has a special role to play. I will talk about it a few slides later. We are using Tomb-Cook 4a. Now, an algorithm can result in optimal performance if it has been designed keeping features of the implementation platform into consideration. So, let us have a look at different platforms. Our modern desktop and laptop processors, they support vectorization. For example, Intel has AVX intrinsics, and using those intrinsics we can process multiple coefficients as a vector. For example, using EPI 16, we can pack 16-bit coefficients in a 256 vector and use vector processing features of modern Intel platforms to compute all 16 operations in parallel. Similarly, there are also EPI 32. We can pack 8 32-bit coefficients in a 256-bit vector, and then we will process only 8 coefficients in parallel. So, this is high-end platform. This platform is ARM CortexM4 microcontroller. This is a resource constraint platform. It's a 32-bit microcontroller, and it has DSP instructions. These DSP instructions allow you to multiply to work on half-sized coefficients. For example, using DSP instruction, we can easily process 16-bit numbers in such a platform. So, these DSP instructions work on 16-bit coefficients. So, what we have in the high-end size in AVX, we can process 16-bit coefficients in a single AVX vector. In the low-end side, we can process 16-bit coefficients using DSP instructions. So, both sides, high-end and low-end, they tell us that if our coefficients are within 16 bits, then we can process them efficiently using AVX and efficiently using DSP instructions. So, we can cover both high-end and low-end platforms. So, there are several options for choosing Q. It should be around 2 to the power 16. There are two things. One is security and another one is efficiency. So, there is also a security reason for choosing a particular value of Q. Now, in this talk, I will say why we choose, how we choose Q to achieve efficiency. Now, all these options, in theory, they look similar, but in practice, they result in different computation time. So, I come back to this Tomb-Cook interpolation slide. This division by 24 has a special role to play. So here it is zoomed in. 24 is 8 times 3. So we can compute the division by first computing a division by 3 and then computing a division by 8. Now division by 3 is easy because we are working in a with a power of 2 modulus, and in power of 2 modulus 3 has inverse. For example, 3 inverse 2 to the power 15 is this. So we can compute the division by 3 as a multiplication by the inverse of 3. This is easy. The problem happens in the division by 8. Since q is a power of 2, 8 is also a power of 2, so 8 doesn't have an inverse. So we need to compute actual division operation. Division by 8 is also cheap because power of 2 using a power of 2 we need to just do right shift operation to do division. But we have to compute actual division. So now we consider the choice q equals to 2 to the power 15. In this case, after the division the result will be 15-bit wide. Now division by 8 involves 3-bit right shift operation. So top 3 bits after the 15-bit will appear here. So here this is okay. This is 101. These are the top 3 bits after 15-bit. After division by 8, that is after right shift operation by 3-bit position, all these bits will appear here. Now if we are working with q equals to 2 to the power 15, then we will have to maintain 18-bit precision in the input data. Okay. Thanks. In that case, we are working with a 16-bit computer, and we will have to work with 2 words, and this makes implementation complicated and also results in slowdown. Now I come to the choice q equals to 2 to the power 13. In this case, we will need total 13 plus 3, 16 bits of precision. So we need to work with only 16-bit numbers. Then we can get a correct result after shifting by 3 positions. That's why we choose 13-bit position. Why not smaller values? Smaller values are also possible, but they will introduce more noise in the system, and that will make a decryption failure higher. There is also a security reason. For the parameter set, we choose q equals to 2 to the power 13, and correspondingly p is chosen as 2 to the power 10. Now in the high level, we implement polymer multiplication using a hybrid structure. First we apply Tumcook, then in the lower level we apply Karasuba, and when the polynomials are enough small, say 16-bit, then we use schoolbook. Why 16 coefficient polynomials are chosen in the threshold level? Because we are working with AVX, and in AVX we can pack 16-bit coefficients in a single vector. So if the polynomials are of size 16 coefficient long, then we can easily pack them in a single AVX vector, and we can process them efficiently using AVX. Now I'll just since there is not enough time, so here are few slides on how we implemented polymer multiplication using DSP instructions. This is multiply and accumulate instruction. It requires 16 instructions if we use SMLA. There is another instruction called SMLA DX. It allows multiplication of crosswords. So we can compute A1 B0 plus A0 B1 in a single using a single instruction. So this reduces number of operations by half, because previously using this instruction we needed to compute 2 multiplications. Here we compute them together. In the overall range, we reduce instruction count by 25%, and then finally we also we use the pack instruction PKHBT to pack 2 neighboring half words, and then also we can reduce some instruction count. For a 16 cross 16 schoolbook multiplication using these DSP instructions, we can achieve around 40% reduction in overall instruction count. Okay, we also did some high level optimizations. They are easy to understand. I will skip them. Finally, I come to the results. On AVX platform, key generation, encapsulation and decapsulation, all operations take roughly 100,000 cycles. For Saber, the secret key size is around 1.3 kilobytes, public key is less than a kilobyte, and ciphertext around 1 kilobyte. On ARM Cortex-M4 microcontroller, if we use DSP instructions, then all operations, key generation, encapsulation, decapsulation, take roughly around 1 or 1.5 million cycles. So this results in around 50 times faster computation with respect to Frodo, because in case of Frodo, there are around 80 million cycles. If we do not use DSP instructions, for example, Cortex-M0 microcontroller, then the computation time increases roughly by a factor of 4. So with this, I will stop. We are also implementing a hardware for Saber, which will be available soon. Thank you.